Hello everyone, welcome to Adson Engineering Academy. It is me, your tutor Adson, and today we're going to continue on our mixed design calculation. So in case you missed the first video, please do watch that and we'll continue from there to the second video. Let's dive in and see how we can solve this particular mixed design calculation problem. Well, in our mixed design calculation for today, we're going to have a look at the second question, and here is what we have. The question says we still need to cast a beam of 100 by 150 millimeter with the overall cross section having a length of 1.2 meters. That means it is still the same as in the previous video. The minimum reinforcement is what we need, but the grade of concrete is given to be M25. Now, first video we did for M20, but in this video we're going to do for M25. So follow with me carefully until you understand what is the difference between the first video and this other one. Now, the grade of concrete is M25, but the one for steel is Fe415. We're asked to prepare the mixed design calculation for the above beam, and additionally 3 more cubes, and each cube is having the dimension of 150 by 150 by 150. The following informations have been given to help you do this mixed design calculation amicably. The grade is M25. The maximum nominal size of the aggregate is 20 mm. Then the exposure condition is moderate. The workability of the concrete we're producing is 100 millimeter slam. So in the first video our slam was 75, but this time round we are using 100. So take note of that. The specific gravity of cement is 2.88. This is what we obtained in our lab only. So we're trying to utilize those values. Okay, we're not taking the values from anywhere else, but the experimental result we obtained from the lab. The specific gravity of fine aggregate is 2.63, and the specific gravity of cast aggregate is 2.86. Water absorptions of cast aggregate is 0.48, and then water absorption for fine aggregate is 1.1%. In this problem still, we don't have admixtures, we don't have any superplasticizer here or retarder. Now, I'm going to take you out to solve this. In my next video only, I will do the one which contains all those, the superplasticizer and the rest of it. So please don't miss the next mixed design calculation too. Let's see how we can do this question. So according to the mixed design calculation, the first thing we do is to calculate the target strength, and since it's for M25, now the formula says FCK, which is our target strength, equals to FCK plus 1.65 S. FCK is this particular 25, the grade that we want to obtain, which is the compressive strength, and then S is the standard deviation, and this is provided in the code itself. And according to IS 10262, it provides that the standard deviation for M25 and M20, both of them are the same, and it is 4. So please check that table, and then you're going to get your FCK of this 25 plus this is coming to 31.6 in MPa. Now, the second option says FCK dash equals to FCK plus X. Now, this X is a factor and it depends on other conditions. Okay. Now, it is also provided is in the code itself, and for M25 is 5.5. Now, 25 plus 5.5, the answer comes to 30.5. Now, out of these two, this one and this one here, the greater is the final value that you consider. So, what we're considering in this case is FCK dash equals to 31.6, because we have 31.6 as our value of target strength, which is greater. Now, second portion says approximate entrapped air is 1% for 20 mm nominal maximum size of aggregate, and this is according to table 3 of IS 10262. So in table 3 only, when your maximum size of aggregate is 20 mm, the entrapped air is only 1%. Okay, so also take note, take this reading from table 3 and you check, you find it's 1%. It varies. If it is 40 mm, it also varies. Okay. The third part is water cement ratio. Now this water cement ratio is what you need to read from the what? From the figure, and that is figure 1. From this curve only, this is what we're calling figure 1. Okay, now our target strength is 31.6. That means it is somewhere here, 31. So when you drop this to the second what? Curve. Okay, now to the second curve is what we are getting. You find that this is not reaching 0.5. So since it is only stopping somewhere here, and you drop this down, I have considered that this is coming to 0.48. Okay, yeah. So 31.6, when you drop it and drop this down, it comes to 0.48 as the value of free water cement what? Ratio. So get your target strength, drop it horizontally until it cuts the second curve. Why are we using the second curve? I explained it in the first video. It is because the cement, the grade of cement that we're using for this particular case is grade 43. So because this one is grade 33, 43 and 53. So we're using grade what? 43 for the cement. Okay. Well, so our water cement ratio is 0.48. That is why I have this. Now, the next thing is the water content. Okay. The water content is obtained from table 4 and it says water content is equals to 186. And this table is only meant for when your slump is 50 mm. Okay. So when the slump is 50 mm, the water content according to your grade and the maximum size provided is what? 186. Now you will say, how do you obtain this? Let me show you that table only. This is the table, water content per cubic meter. So the nominal size is 20 and the water content is 186 kilogram. Remember, it is in per cubic meter. Okay. So since we have obtained that, now what brings the difference is that this case we're using slump of 100. Okay, not 75. So since it is 100 and this 186 is only for 50 slump, so that means 100 minus 50 slump, 50 will give us what? 50 extra. So there is 50 more extra that needs to be accounted for. Okay, but for every 25 increase in the slump, okay, for every 25 that will be added to this 50, you have to increase the water content by 3%. Okay, so if 25 is 3%, what about 50? So that means 50 will be 3 by 25 times 50. So you realize that this is 2, so it will be 6%. Okay, that is why I've said then increase it by 6%. I hope you have understood that point clearly. So 186 plus 6% is 6 out of 100 times 186. Water content is producing 197 in terms of kilogram, and it is in per cubic meter. So in part number 5, we are looking at cement content, and according to table 5 only, the cement content is given by the water content divided by water cement ratio. We have got both of them. Water content is 197 and water cement ratio is 0.48. So when you divide this, the answer is 410.42 kilogram, and this is also per cubic meter. Now, according to the table only, it provides us the value of minimum cement content for the moderate exposure. According to that, so look at the table first of all. Okay, and we're considering the beam, which is a reinforced concrete, that we're going to take into consideration. Now, if it is a minimum cement content, that means according to the grade of concrete that we are having. So you realize that this is grade M25, and under minimum cement content, we're taking what? 300. So read it carefully. Grade M25, cement content minimum is 300. Okay. then this 410.42 that we have obtained is greater than this. It's okay. The next step is proportion by volume of coarse aggregate. In proportion by volume of coarse aggregate, now here you also need to observe carefully because there is slight difference from what we got in our first video only. Now the aggregate is of zone 2, same. And I told you in our first video about this topic only that according to how we obtain this zone 2, according to what? The sieve number 0.6 mm. Okay. Water cement ratio of 0.5 produces the volume of coarse aggregate of 0.62. If the water cement ratio is only 0.5, the volume of coarse aggregate is 0.62. Where did you get it from? This is from the table on table 5 under zone 2. Now in zone 2, look at this table carefully. Zone 2, if your maximum size of aggregate is 20, you will produce the volume of coarse aggregate as 0.62 under zone 2. Okay, well, so that's what we have obtained, but our water cement ratio is 0.48, not 0.5. So that means there is needs for adjustment. Take a key note here. Volume of coarse aggregate is increased at a rate of 0.01 for every decrease in water cement ratio by 0.05. So I will explain that to you here slightly. Now look at this. If we have 0.01 is equivalent to 0.05, I mean, is equivalent to 0.01. What is our decrease? Because we have 0.5, which we know the value, but our water cement ratio is 0.48. So the difference is 0.5 minus 0.48. What do you get? You get 0.02. Okay. So if that is the case, then if the water cement ratio of 0.05 is equivalent to the volume of 0.01, if that means the rate at which the volume will increase. If there is a decrease in this, there will be increase in this. Okay. So the difference is 0.02. That means it will be 0.01 divided by 0.05 times 0.02. You get 0.04. This will be the total amount that we need to add to 0.62, because we have this water cement ratio of 0.5 is equivalent to 0.62. But since there is a decrease in water cement ratio, there should be increase in the volume of coarse aggregate. So whatever we have got is 0.004, then we shall add it to 0.62. We get this. This is volume of coarse aggregate. Okay. Then volume of fine aggregate will be 1 minus that volume of coarse aggregate, which this will be the what? The answer. I hope you've got that part clearly. In our mix calculation, total volume is 1 meters cube. The volume of the entrapped air, it was 1%. Now, in terms of volume, is 0.01 meters cube. Volume of cement is equals to mass of cement out of specific gravity of cement times 1 by 1,000. The answer is 0.142. Volume of water is equals to mass of water that we got out of specific gravity of water, which is 1 times 1 by 1,000. You get 0.197 meters cube. Volume of all-in aggregate is equals to A, our A is this one, minus B, which is this, minus C, which is this, minus D, which is this. So that volume of all-in aggregate is coming to 0.651 meters cube. Let's see, what about the mass of fine aggregate? What is the formula? It's equals to volume of fine aggregate times volume of all-in aggregate times specific gravity of fine aggregate times 1,000. So our volume of fine aggregate, we obtained 0.376. Volume of all-in is 0.651. Specific gravity of fine aggregate is 2.63 and times 1,000. Okay, don't forget that, times 1,000. So the answer we're getting is 643.8 in terms of kilogram. Okay. Well, what about mass of coarse aggregate? Is equal to volume of coarse aggregate times volume of all-in aggregate times specific gravity of coarse aggregate times 1000. So this is 0.624 times volume of oil in aggregate times specific gravity of coarse aggregate times 1000. We're getting 1161.8 in terms of kilogram. So let's have the mixed proportion of M25 according to water cement ratio of 0.48. Cement, fine aggregate, coarse aggregate. The mass that we obtained for cement was 410.42. The mass for fine aggregate is 643.8. Then that for coarse aggregate is 1161.8. When you divide each of them by the mass of cement, you'll obtain this ratio 1. Then you obtain this 1.56. You'll obtain this 2.83. The total ratio, this plus this plus this, gives us 5.39. Now, this is where the task lies. The task is, we need to cast one beam. The dimension is 100 by 150 by 1200 in mm. And 3 more additionally alongside the beam. We have to cast 3 cubes, each of them 150 by 150 by 150 in terms of mm. Okay. So the total amount of the materials required, that means combine the cement, the fine aggregate, the coarse aggregate, plus the extra that we're going to take into consideration. So let's have the total amount of materials first. I'm casting one beam. And what is the volume of that beam? It's 0.1 times 0.15 times 1.2 times, since we are considering reinforced beam, so we take the unit of 2500. So 2500 is what we are going to multiply with. But for the cubes, we shall take 2400 because it is not going to have any reinforcement. 3 cubes times the volume times 2400. Now this is going to give us the amount of material that we need to measure or take it into that batch, which is 69.3 kilogram. Now, you have to provide extra. We provide 20% extra. And this 20% extra is 20% of the total material. So we have 69.3, which is the total amount. 20% of that is 20 by 100 times 69.3. The answer is 83.16. Now, each material, what should be the amount that I should measure? Okay, so cement, the ratio of cement, we found that it is 1. So it is 1 out of the total ratio times the total amount of material required. The amount of cement that we are going to measure therefore is going to be 15.43 in terms of kilogram. Now let's talk about fine aggregate. The ratio that we obtained for fine aggregate was 1.56, and from that only, this divided by total ratio times 83.16, we obtained that to be 24.07 in terms of kilogram. Coarse aggregate, 2.83 was the ratio out of the total, which is 5.39 times this, you obtain 43.66 in terms of kilogram. But for the case of well-graded coarse aggregate that we need to consider, I'm considering the ratio of the coarse aggregate, which is 20 mm down to 12.5 mm down in the ratio of 70 to 30. So I'm taking 70% of this to be 20 mm down. Then I'm taking 30% of this coarse aggregate to be 12.5 mm down. So that means coarse aggregate 1, which is 70%, is 0.7 times the total amount of coarse aggregate, which is 43.66. The answer is 30.56. Then coarse aggregate 2, which is 30% of this, that is 12.5 mm down, 0.3 times 43.66, you obtain what? This. Now let's talk about what should be the amount of water. In most cases, people at the site, they try to estimate just because they want to obtain the workable concrete, they just add in any way they feel like, so long as they have obtained a workable concrete. But that's not the case. You have to calculate and know. How do you calculate the amount of water or the water required in mixing a particular batch of concrete? So this is the mass of water that we obtain, 197. Multiply it with the volume only, which is 1 times I'm having only one beam. Okay, so times 0.1, which is the dimension of the beam, times 0.15 times 1.2. Now this is for the beam, the total volume of the beam. That's only one beam. And then I have 3 cubes. So 3 cubes times the volume of each cube, which is 0.15 times 0.15 times 0.15. That's why I've put here on the cube. Hope you understand that. So this is giving us 5.54, and you can measure this in terms of liter, no problem. Okay. Well, now extra water should be provided. Why? Because there is possibility of absorption of water by this aggregate, by both the fine aggregate and the coarse aggregate. That's why in our question earlier on, they have given us the absorption by fine aggregate and water absorption by coarse aggregate. So we need to provide extra water for that. So water absorption for fine aggregate was given to be 1.1%, and that is the same as 1.1 by 100 times the mass of fine aggregate that we have obtained, which is 24.07. So 24.07 times 1.1%, which is the same as 1 by 1.1 divided by 100. Then for coarse aggregate is 0.48%, which is the same as 0.48 divided by 100 times 43.66. So this is what we have. So that means our extra water is coming to 0.475. So add it up to this water that we have obtained. That will give you the total amount of water that we require for casting one beam and 3 cubes. In summary, this one beam and 3 cubes would require 15.43 kilogram of cement, then fine aggregate 24.07, coarse aggregate 30.56, then coarse aggregate 2, that is 12.5 mm down, 13.1 kg, then water is 6.015 in terms of liters. Thank you so much for watching that video till the end. I hope you have enjoyed it. If it is important and helpful to you, please do like the video, comment, and above all subscribe to Hudson Engineering Academy so that you don't miss any of my videos.